This is the third video in a course of abstract linear algebra, and we're still a few videos before we start looking at the standard objects from linear algebra. But that being said, I think we'll have a stronger background if we hold off just a little bit longer. So our goal today is to eventually look at the notion of a group. And we want to understand the notion of a group because our main object of study later will be something called a vector space, which is in fact a special type of a group with some additional structure. Okay, so we're going to build the notion of a group slowly from one piece at a time, starting with something called a magma. So a magma is a set M together with an operation which I'll call star, and that operation has two inputs and a single output. So in other words, you take two elements from M, you combine them, and you get another element from M. So generally we write it as follows. So for all M and N in M, M star N is also in M. And I want to notice here that there's no restrictions on the structure of this star operation or anything else going on in the magma at all. All you need is a set and an operation, nothing else. So let's look at a couple of examples of magmas before we move on to our next structure. So the first will be R3. Well, maybe before we get started, notice we need to define a set and an operation in each case. So first of all, our set will be R3. So that's all ordered triples, A, B, C, where A, B, and C are real numbers. And then our operation is defined as follows. So A, B, C, star, X, Y, Z. So that takes an element from R3 and it's combining it with an element from R3. And that will give us BZ minus CY, CX minus AZ, and AY minus BX. So that's another element from R3. And if you've seen something called the cross product before, this is in fact the cross product, although you need not know that at this point. So let's do an example of this real quick. So let's maybe take the element 1, 2, 3, and we'll star it with the element 1, 0, negative 2, and see what we get. Okay, so let's see, we need BZ, so that would be 2 times negative 2, minus C times Y, so that's 3 times 0. So really just we have 2 times negative 2, so that would be negative 4 in this entry right here. And then let's see, CX minus AZ. So that's going to be 3 times 1 minus 1 times negative 2. So that's going to be 3 plus 2, which is 5. So we have 5 of this entry right here. And then finally, AY minus BX. So that'll be 1 times 0 minus 2 times 1. That'll give me minus 5. So if we were to combine the elements 1, 2, 3, and 1, 0, minus 2 with this operation, we would get minus 4, 5, minus 2. Okay, for our next example, we'll take the set to be the set of real numbers, and our operation will be the application of the following two variable function. So I've called it f of xy, and it'll be x cubed y plus 2x squared. And so here we'll have x star y is just x cubed y plus 2x squared. Okay, well we can do an example here as well if we wanted to. Let's maybe do 2 star 5. So that means the role of x is being played by 2 and the role of y is being played by 5. So that's going to give us 2 cubed times 5 plus 2 times 2 squared. Well, that's pretty easy to calculate. We have 8 times 5, which is 40, and then plus another 8, so this will be 48. So here we've combined 2 and 5 to give us 48. And we can generalize this second example pretty easily by taking A to be any set and the operation to be any function from A cross A to A. And so here, if we've got A and B in capital A, we have A star B is equal to F evaluated at AB. So I think these are three nice, simple examples of magmas. Now we're ready to move on to our next structure. For our next structure, we'll look at something called a semigroup. So by definition, a semigroup, which I'll call S, is a magma where the operation is associative. So let's recall that magmas did not require the operation to have any structure. Here we require that it is associative. So let's recall what that means. That means for all A, B, C, and S, if we group in the following two ways, we get the same answer. So in other words, A star, B star C is the same thing as A star B star C. So many operations that you know from arithmetic are already associative. So let's look at a couple of examples. So let's start with the natural numbers. And so by the natural numbers, I mean positive integers. So like 1, 2, 3, 4, 5, so on and so forth. And my operation is addition. So very clearly addition is associative, kind of from grade school arithmetic. We have A plus B plus C is the same thing as A plus B plus C. Let's also notice that this operation is commutative. And what I mean by commutative is that A plus B is the same thing as B plus A. That's a little bit of a bonus here. That's not a requirement. You would maybe call this a commutative semigroup or maybe an abelian semigroup. But we'll get into that terminology a bit later. So maybe a little bit more interesting of an example would be the set of all words in the alphabet A, B, C, D. So by words, I just mean strings of letters in that alphabet. So like A, B, A, C, D would be an example of a word in that alphabet. So that would be an element of the set. And then my operation is concatenation. So that means I kind of just smash two words together. So I've got an example here, A, B, D. So that's a word in my alphabet. Star, C, A, B. That's another word in my alphabet. Will give us the following word, A, B, D, C, A, B. So we took two words here, combined them to get a single word. Okay, so now let's move on to our next structure. So our next object will be something called a monoid. So a monoid, which I'll use the letter M, is a semigroup with an identity element. So what do I mean by an identity element? I mean there's a special element, I'll call it E in M, such that M star E is the same thing as M, which is the same thing as E star M. So in other words, combining this identity element with any element of the monoid does not change that element of the monoid. So let's look at two examples of that. So my first example is the set of all functions from A to A, where A is any set. And so earlier we saw that composition of functions like this was indeed associative. So we have an operation, composition, it's associative, so that makes it a semigroup. And it is also has an identity, that makes it a monoid. The identity is indeed just the identity function. So that's the function that takes every little a to itself. So my next example could be built off of something that we just saw, and that is the natural numbers, but now we include the number 0. So in other words, it's all numbers 0, 1, 2, 3, so on and so forth, all non-negative integers. And here my operation is addition. So clearly we've got an operation, it's associative because of standard arithmetic rules. And then 0 satisfies the rule that n plus 0 is just equal to n. And that's the same thing as 0 plus n. So we do have an identity. Okay, so now that we've done all of this, we're finally ready to look at the notion of a group. All right, now we're ready to look at the notion of a group. So we've built everything from the ground up. We only need to add one more requirement in order to have a group. So a group G is a monoid where every element has an inverse. So what do I mean by that? Well, I mean that for all little g in G, there exists something that I'll call G inverse in G, such that if you star G and G inverse in either order, you get back to the identity element. So an inverse is like a path back to the identity element. So it doesn't make sense to talk about an inverse unless you have an identity in the first place. So let's look at some examples of groups. So We're not going to go quite into the depth of examples of groups and structure of groups in this course because we're doing abstract linear algebra and we're really just building enough so that we can carefully study linear algebra. But if you're interested, group theory is a vast area of study that you could look at on your own. Okay, so here are 4 examples. So the first is the set of integers, and I guess I should say here, my operation is addition. So you can easily check that we have associativity here, we have an identity here, which is 0, but we also have inverses. Notice that any integer n has an inverse, which is the negative of itself. So n plus negative n is equal to 0. So for instance, like 3 plus negative 3 is equal to 0. So 3 and negative 3 are inverses. So here's another example. So this is maybe r with a cross here. So this would be like multiplicative real numbers. So that's going to be all real numbers except for 0. And like I said, my operation will be addition. And so here the inverse will just be the reciprocal. So for instance, 2 times a half equals 1 because my identity in this case is the number 1. Okay, and we had to take 0 out because it doesn't make sense to take the reciprocal of 0, so 0 would have no inverse. Okay, then this is a callback to our last video where we looked at something called the set of permutations. And in fact, the set of permutations is a group. It's called the symmetric group. Let's recall that that's all bijections from the set 1 to n to the set 1 to n. And it had inverses and it had an identity. But the fact that these were bijections implied that we had inverses in the first place. Now here's another small example. This is the set of 4 complex numbers, plus minus 1 and plus minus I. And in fact, this forms a group. If you take multiplication of these elements, you land back in the set. And everything has an inverse. So let's notice that if we take I and we multiply it with minus I, we'll get minus I squared, but that's minus negative 1, which is positive 1. So in fact, I and minus I are inverses. And you can check that like 1 is the inverse of itself and negative 1 is also the inverse of itself. So everything in here has an inverse. Okay, so let's clean up this part of the board and we're going to look at another example. So we're going to look at one last example before we prove some general results involving groups. And that example is Zn, or the integers modulo n. But we're not going to look at any of the number theory underlying this. We'll instead take a more basic approach. So let's define Zn to be the following symbols. So 0 bar, 1 bar, 2 bar, all the way up to n minus 1 bar. So let's notice it has exactly n elements. And then my operation will be this type of addition. So I'll define it by a bar plus b bar to be the remainder of a plus b when dividing by n. So let's look at some examples real quick. So let's say we're inside of Z8. So notice Z8 will have the numbers 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, and 7 bar. Those 8 numbers. So let's see. If we wanted to, for instance, do 5 bar plus 6 bar, we would need to find the remainder when dividing 5 plus 6 by 8. So let's write that out. So the remainder when dividing 5 plus 6 by 8. Well, notice 5 plus 6 is 11. If we divide 11 by 8, we get a quotient of 1 and a remainder of 3. So that means here we get 3 bar. Maybe I should put here, this is the bar of this. So 5 bar plus 6 bar is equal to 3 bar. And then let's maybe do another example. Let's maybe do 7 bar plus 7 bar. So notice that's going to be the remainder when dividing 14 by 8, but the remainder when dividing by 14 by 8 will be 6. So this will be equal to 6 bar. You guys can play some more examples of this if you'd like to. Okay, so maybe I haven't shown that this is exactly a group, but I'll leave that as a homework example or a homework exercise. So this is a group. So let's notice we very clearly have an identity element. That's this 0 bar. And then also we know that this is closed under our operation because the only possible remainders when dividing by n are 0 to n minus 1. So that's good. Then associativity just comes from the fact that addition is associative. So really all you have to check is that the inverses are here. That's the only thing that I haven't commented on. So before we move on to some general results, let's look at something called a Cayley table for a group. Maybe we'll use Z5. For a more in-depth example, let's look at Z5. So that's going to be the numbers 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. So we'll take our operation as defined up here. So that'll be the remainder when dividing the sum of two of these by 5. So I'm going to look at an addition table for this group. And anytime you look at some sort of multiplication or addition or really operation table for the elements of a group, that's called a Cayley table. So what we're making is a Cayley table for the group Z5. We want to look at all of the ways to add elements of Z5. So let's notice if we take 0 plus anything, then we don't change anything at all because 0 bar plus 0 bar will still be 0 bar. Here we'll still have 1 bar, 2 bar, 3 bar, and 4 bar. That's because the remainder won't change if you add 0. And then down this line, it's the same thing. So 1 bar, 2 bar, 3 bar, and 4 bar. In fact, 0 is the identity element. Now let's see what happens for 1. So 1 plus 1, so when we divide 1 plus 1, which is 2, by 5, we get a quotient of 0 and a remainder of 2. So this is going to be 2. Likewise, this will be 3 bar, this will be 4 bar. But if we add 1 and 4, we get 5. That remainder will be 0. So here we've got 0 bar. That looks like a 6, but that should be a 0. And then likewise down this column, we get 3 bar, 4 bar, and 0 bar. And now you can start to fill it in pretty easily. So notice 2 plus 2 is equal to 4. 2 plus 3 is 5, which is 0 in this case. 2 plus 4 is 6, but 6 has a remainder of 1, so this is going to be 1 in this case. Then we can move down this way as well. So 3 plus 2 is 5, which is 0, and then here we have 1 again. Then 3 plus 3 is 6, but 6 is 1. And then 3 plus 4 is 7, but dividing 7 by 5 gives us a remainder of 2. So we get 2 bar here, 2 bar here. And then finally 4 plus 4 is 8, but dividing 8 by 5 we get a remainder of 3. So this is a filled in Cayley table for the group Z5. And let's notice that this group is in fact commutative. In other words, A bar plus B bar is the same thing as B bar plus A bar. And that makes this group something called abelian. So let's maybe add that over here. So if maybe G star H equals H star G, for all G and H in G, we say G is abelian. So it's an abelian group. Okay, so like I said, now we're ready to do some general results. Now we're ready to prove our first result, and that's a cancellation rule. And that says if we've got a group G and 3 elements A, B, C that satisfy the following condition, AB is equal to AC, then B is equal to C. So we can cancel this A from both sides. And I want to point out here that I have made my notation a little bit more efficient. Instead of writing A star B, I'll write A, B, like it's A times B. And this is pretty standard if you're working with arbitrary groups or multiplicative groups. If you're working with groups where addition is the operation, you generally leave a plus in there. And then likewise, we've got a right cancellation rule as well. So if AB is equal to CB, then A is equal to C, but maybe I'll leave that one for you guys as it follows almost exactly the same way. Okay, so let's see this proof. So let's suppose that AB is equal to AC. Now, since we're in a group, everything has an inverse. In particular, A has an inverse. So let's take this and we will left multiply by A inverse. So let's see what that gives us. That'll leave us with A inverse times AB is equal to A inverse times AC. But now we can't quite cancel the A and the A inverse until we reassociate. And we're within a group, and so we know the operation is associative. So let's use associativity to rewrite this as A inverse A times B equals A inverse A times C. Then finally, A inverse times A is the identity. So that tells us that the identity times B is the same thing as the identity times C, but the identity times B is B, the identity times C is C. So we have arrived at B equals C, which is exactly what we wanted to end at. Like I said, I'll let you check the right cancellation on your own, and we're going to move on to another general result. Now we're going to look at a proposition which proves a lot of fairly standard, simple general results involving groups. So it has 5 parts. The first part is to show that the identity element of a group is unique. So let's get cracking on that first part. So let's suppose that we have a group G, and E and F in G are identity elements. So I'll put the S in quotes I'll put the S in parentheses because in fact what we'll find out is that E must be equal to F. So in other words, if it looks like we have 2 identity elements, then there is in fact only 1 identity element. And the interesting thing here is we can do this all at once. So let's start with E. And notice that E is going to be the same thing as E times F. So this equality is because F is an identity. But that's going to be the same thing as F. And this equality is because E is an identity. So like I said, here we have equality because F is identity. Here we have an inequality because E is an identity. But kind of removing the middle bit of that, we see that E is equal to F. So if we try to have more than 1 identity, we in fact end up with only 1 in the end. Okay, so that means we've proved this first result. And now let's move on to the second one that says inverses are unique. So let's do that by starting off with an element A from the group and B and C from the group such that they are both inverses. So in other words, we know that AB is the same thing as BA, which is the identity. Inverses act from both sides. And we know that AC is the same thing as CA, which is also the identity. So in other words, we're starting with an element from our group, and we're saying that we might have more than 1 inverse, and we want to end up with there is really only 1 inverse. So we should end up with B is equal to C. Okay, so let's maybe see how we could do that. Let's start with B and see if we can use these equations right here to get us all the way to C by itself. And I see a way to do that pretty easily. Notice that B is the same thing as B times the identity, but we can rewrite the identity using this equation right here as A times C. So we have BA times C. Maybe we should be careful about our associativity here. Here we've got the associativity like that because we replaced the identity with A times C. And now let's reassociate to BAC, again, because of associativity. But BA is also the identity. So we have this is the identity times C, which is just C by the definition of the identity. So we started with B, we ended with C, but that's everything that we needed to prove this second result. Okay, now let's prove this third one, which says the inverse of A inverse is back to A. Okay, so let's get going. So let's start by observing that A times A inverse is equal to the identity. But then that's also the same thing as A inverse inverse times A inverse. But now we can use our cancellation rule that we did before to cancel the A inverse from both sides, and we'll be left with A equals A inverse inverse. That's really all there is to this one. Okay, so now let's move on to the next. Okay, so our next result is sometimes called the shoes and socks theorem. So it tells us that AB inverse is the same thing as B inverse A inverse. So in other words, if we invert something in parentheses, we have to change the order. Okay, so how could we do this? Well, let's maybe notice that we could take AB inverse times AB. And see, that's the same thing as the identity because we're multiplying something by its inverse. But now we can take this identity and rewrite it as B inverse times B. And then furthermore, we can take that and write it as B inverse times the identity times B. Then take that identity in the middle and write it as A inverse times A times B. So let's just see how this went. This identity spread out into this A inverse times A, and this identity right here spread out into this B inverse times B. Okay, but now let's do a little bit of grouping here. We can kind of freely group because we have associativity. So this is going to be the same thing as B inverse A inverse times AB. But now let's look at the extreme left and right hand side and notice we can use our cancellation rule, which we just proved, to cancel the A times B from both sides. And that gives us AB inverse is equal to B inverse A inverse as needed. Okay, so that proves this next to last result. And now we're ready to look at this last one, which says if we take A times A and get A, then we must know that A is in fact just the identity. This again is pretty quick, just like all of these were pretty quick. So let's take this, A times A equals A, and let's rewrite that right-hand side as A times the identity, and then use our cancellation rule. So we can cancel this side and this side. So that's going to give us A equals the identity. So I guess I just did this forward direction. You could do the reverse direction very quickly. Notice that if A equals the identity, then the identity times itself is definitely equal to the identity. So we're good to go in that reverse direction as well. Okay, so I'm going to introduce a little bit of notation involving repeated applications of the group operation, and then I'll leave you with some warm-up problems. So the last thing we'll cover is some notation. So in multiplicative groups, we'll write g to the nth power to mean g starred with itself n times, just like from classic multiplication from maybe arithmetic. So if you're, for instance, in non-zero real numbers, if you take 2 to the 5, that's the same thing as 2 times 2 times 2 times 2 times 2, which is the number 32. We combine 2 with itself 5 times. But maybe more interestingly, if you take the 3 cycle 1, 2, 3. So writing that three cycle squared, so this is in S3, is going to be the same thing as applying 1, 2, 3 to itself like this. And then by calculation methods that we saw in the previous video, we saw that that would turn into the 3 cycle 1, 3, 2. I'll let you guys check that if you need to. Now in additive groups, instead of writing as an exponent, we write it as a multiplier. So n times g is the same thing as g plus g plus g, n times. So for example, if we take 5 times maybe 3 bar, and let's say here we're inside of Z4, that's going to be the same thing as 3 bar plus 3 bar plus 3 bar plus 3 bar plus 3 bar. And this is inside of Z4. So let's see, 3 bar plus 3 bar is equal to, well, 6 divided by 4, keep the remainder, so that's 2. So this is going to be the same thing as 2 bar. And then likewise, 3 bar plus 3 bar is another 2 bar. And then this 3 bar will be one last 3 bar. And now we can take 2 bar plus 2 bar. Notice we get 4. Divide that by 4, we get a remainder of 0. So in the end, here we get that this is 3 bar. So notice I was careful to put a bar over the 3 here, but not over the 5. because what I'm mimicking here is this exponentiation, this repeated application of my group operation. Okay, so all of that's good. Now I'm going to give you guys some warm-up problems. So I've got 4 warm-up problems for you. So the first is to show that if a squared is the identity for all elements A in a group, then that group is in fact abelian. Let's recall abelian means that the operation is commutative. Next is to prove that A inverse B A all to the n power is the same thing as A inverse B to the n A. And that actually makes this operation really, really natural. This is called the conjugation of B by A. We'll see that later in the linear algebra component of this course. Next, what is the inverse of this product of n elements? So we've got A1, A2, all the way up to AN. So we did this for 2 elements already, so you just need to extend that. Finally, let's make a Cayley table for the group Z6. Let's recall that that's going to be everything 0 bar, 1 bar, up to 5 bar, where you take addition and then keep the remainder when dividing by 6. Okay, that's a good place to stop.